Hello students, you know who this is. It's Professor Dr. Mink, and it's time for another exciting CSC2 lecture. The topic at hand is the content from Chapter 22, Sets and Maps. Set is a collection of elements with no duplicates, and in a set there should be no other relationship assumed among the elements. A map is a collection that establishes a relationship between keys and values. The goal is to have an efficient way of obtaining a value given its key. Earlier in my career, I did some relational database work, and the primary key is the sole identifier for every record in a database. You're probably used to this format by now. We'll start off looking at the Java API set and map collections, and then we'll turn our attention to how sets and maps are used to solve problems, and then the implementation of sets and maps, and the last topic will be hashing, which we'll get to. I don't want to overwhelm you at this point in time. A set is a collection of elements which has no duplicates. We should not assume any other relationship among the elements in a set. And a set's primary purpose is to determine whether a particular element is a member of the set. There are other collections, such as lists, that can test for containment. But if that operation is important, not important, consider using a set. There are several operations that can be performed on a set. In this slide, we have a summary of the methods that we'll be implementing and using. And I'm not going to read all of them to you, but we could pick a few. Is empty. Hey, that looks familiar. Returns a Boolean and returns true if the set contains no elements. Equals compares the specified object passed to that method with this set for equality, which we'll talk about later. Clear removes all the elements from the set. Add adds the specified element to the set if it's not already present. Okay. So we're going to now take a closer look at sets. We'll look at an implementation. You know the routine. We're pretty far along in this class, so let's get started. Here's two more methods that just didn't fit on the previous slide. One of interest is toArray. Returns an array containing all the elements in the set, but we're going to get into this in an implementation demo, so stay tuned. A map is a collection that establishes a relationship between keys and values. I've got some experience with relational databases, and in each table in a relational database there is a column that is, for each record, there's a column labeled the primary key, and that key is a non-repeated value that uniquely identifies each record in the database. So in a map, the goal is to have an efficient way of obtaining a value given its key. So the keys have to be unique, but multiple keys could map to the same object. So an example in a membership ID, a string, could be the key used to retrieve a member object. So that, I don't want to get into too many relational database, but that primary key might also point to another record in a different table. And as with sets, we have a method summary that describes the operations that we can perform on a map. Clear, contains key, contains value, equals, is empty. No big surprise there. I think there's a few more on the next slide. So I'd like you to take a look at these, but we're going to be looking at implementations. So you should be familiar with all of these. It's a continuation of the operations performed on a map. This is a continuation of the methods. There's size, put all. Yeah, we're gonna look at these. So next, we're going to look at a coded implementation that uses sets, and we're going to create a set to test for containment. We have an input file that contains a list of blocked domains, URLs, and we'll test to see if whatever the user inputs is contained in the set. And the set is going to be represented using a tree set object from the Java API, which we'll look at as we explore this in a live demo next. Now we're going to take a look at an implementation of a set, and we're going to use the tree set class. And this is a program that imports a text file, blockdomains.txt, that has this list of blocked domains. Pretty straightforward. And it's going to put those into a set, and then it's going to prompt the user to enter a domain name, and it will check the set for containment. And either the set contains that block domain and it will tell the user so, or it doesn't. So let's go through this. This is the domain blocker class. We set up a tree set of strings, old block set, or named block set, and simply we set up a new file scanner. A new scanner with the input file blockdomains.txt, and while scan.hasNext, we're going to add the next line in that text file, the domain name, to the set. Pretty straightforward. And we have this other method that returns a Boolean. Domain is blocked, and we pass the domain name as a string, and it calls contains, and it either finds it or it doesn't. Pretty straightforward, not a very complex program. Let me see what we're looking at here. Domain blocker, domain checker has the main in it, and our list. So I'm going to run this with a breakpoint in debug mode, and we will take a look at. So I put this breakpoint right after we create the new domain blocker, and it will go in and extract those values from the file. So here we go. If I look at the memory, there's my set. And we have all of the domain names stored in the set. Look at that one. I added that, drminkaschool.com. That's blocked. So let's now walk through this. Okay, enter a domain and done to quit. And where's our output? So we'll say Dr. Mink is cool. Cool. Is that .com? We'll see. Okay. Didn't type done. If blocker dot domain is blocked. Else print out. Okay, that's going to and here we go. We should have that domain is blocked because it is contained in the set. Fairly straightforward. I'm going to give you these files. Up next is going to be an assignment, a set assignment that's going to be much more complex. So I encourage you to download these files, walk through it, get a feel for what's going on. You know the routine, ask questions, etc. Okay, students, you know who this is. This is Programming Project 22.2 from page 828 in your textbook, but it is my version of that project. I've added quite a few details to the project. So I've got it labeled P22.2a. And what this does is it imports two text files. One text file has a list of every name of every United States president. And it stores it in a set. Then it imports a second document, text document, into a second set that holds the name of every vice president of the United States. And then I've built this driver interface where we can add a vice president, we can add a president, we can find a president, we can list presidents, we could list vice presidents. And this is probably the most complex option on the list. It does an intersection of the two lists. It finds all the names of individuals who were vice president and then became president. And there's various circumstances that would have that happen. Died in office. If the president died in office, the vice president becomes president. If the president was assassinated, which unfortunately we've had a couple times in this country. If the president resigned, which is only once, but it did happen. Or if the vice president ran in a general election and won after they had been vice president, won the presidency. So anyway, this generates a lot of data. It's a long list. So what I'm going to run first is I'll run a list of all the presidents. That's option 4. And I'm going to have to restart this a couple times. And there you go. There's all of the presidents listed from George Washington to Donald Trump. Then I'm going to run a list of all vice presidents. And these individuals are less recognizable. John Adams, Thomas Jefferson, they're recognized names because they later became presidents. But George Clinton, Elbridge, Gerry, and then if you go down to, we have Mike Pence, Joseph R. Biden Jr., Dick Cheney, Al Gore. You probably don't even remember Dan Quayle. Anyway, some of these individuals in the later throes of this list did become president. So then if I run 6, it's going to run the intersection. There were 14 individuals who held the role of vice president and president. And here they are. And I mentioned their various circumstances. So let's talk about the implementation of this. And I've got some details that you can see. I'm not going to give you anything to start with. Okay, you've got your linear node class. You've got your linked set, which is based upon the linear node. And here are all the members of linked set. And I'll have a rubric, obviously, for these. Intersection, there's the intersection, is empty. Iterator. Some of these add, you're going to have to code these, but we're not going to use them in this demo. Maybe I'll make that some extra credit. Let me think about that. Okay, and then I've got the interface. Set ADT, which it's the interface, public interface for the link set. And then my driver program just has the main, and it presents this this menu. Some other options, if I come down here and I exit or enter, let's see if we can find. Let's see if we can find a president named John. Okay, John Tyler is found in the set. Remember, there are no duplicates in a set. If I try to find William, okay, not contained in the current set. Although if I add a president, if I add okay, and then I list the presidents. Now remember, there's no relationship between these. They just happen to be imported into the set in the order in which they were president. But now if I list the presidents, you're going to see that person who happens to have the same name as me is now a member of the set. Obviously, if I try to find is found in the set. Let's see, find list. Yeah, I think that's it. If I I can add a vice president too. Let me see. Let's add a vice president. Oh, I think that should be. It should say add vice president, but anyway. So now if I list vice presidents, you'll see I'm vice president. And now if I choose menu 6, there are now 14 individuals who, obviously this is not a real scenario and I'm never going to run for president. But now that name, my name, is now on the intersection list because I added it to presidents and vice presidents. Obviously exit terminates the interface. I'm going to stop this. I might do a second video, just give you a little bit more information on this, and I'm going to give you lots of printouts from the output and a rubric. So as promised, here is a follow-up video that will give you a little bit more information. I'm going to show you the members of each of these classes. There's a linear node class. You can see get element, get next, set element, set next, and element holds the element, and next is the linear node. That's how it's linked. Get your link set, which has quite a collection of members. Some of these are not used in the program. Obviously, you're going to use add, intersection is empty, iterator, size, toString. Don't believe, no, obviously we're not using union. So a link list iterator, which provides you has next, next, remove, etc. So, and the interface, pretty straightforward. It's just one collection, the empty collection exception, which I think I've, yes, I think I've coded enough validation in this to make sure that is not thrown under normal conditions, normal execution of the program. So anyway, wanted to give this to you or let you see this pretty significant or challenging project. So don't procrastinate. And if you have any questions, obviously, you know how to get a hold of me. Pretty easy. Now we're going to take a look at a program implemented using maps to keep track of product sales. And I just want to recall or remind you that a map is a collection that establishes a relationship between keys and values. So we're going to have a key for each value. Suppose that each time a product is sold, its product code is entered into a sales file. Our example is going to read the sales file and update product sales summary. Tree map is what we'll use to map the product code to the product object, and the product code is going to be the key. And we're moving closer and closer towards the concept of a database, a table in a database. Now we're going to take a look at a map. I'm going to give you the files, the source code files for this implementation, but we'll go through it real quick. This is the product sales program, and here's the class, the product class. It implements comparable, and we have a string, that's the product code, and we have an integer that represents sales, the number of items that have been sold with that product code. And there is a there's a file that we have. I'll show you. You got to generate the data file with this other data file creator. It's real quick and easy. But if I go down to this and I show you the sales data.txt, it has hundreds of entries of sales of these are all product codes. These are the key in this map. So what we're going to do is we're going to scan this file. It's over 1,000. Now I can't remember the number, so I got to know. It's 1,383 entries in this product sales. So where is, yeah, so here it is. So, and where is it? Product sales program creates a tree map, okay? And the object has a string and a product sales. I'm sorry, string, product, and we have a scanner. We scan that file. We use the hasNext method, and we just add all of those sales of each product code into the tree map. So I've got a breakpoint right here. Let me run this just so you can see. I'm going to run it in debug mode so we can get to there and look at our variables. So here we have our sales. There were 20 different product codes in that product sales text file. Now remember, there were 1,380 entries in the product sales text file, but they represent only 20 different products. So if I look at the first item in this tree map, okay, product code BR742, and there were 82 sales of that item. If we go back here to the second element in this map, product code BV693, there were 63 sales. So the way this works is, if the product is null, in other words, we can't find, right? We go to sales.getCode and we add that to product. If that's null, we're going to put a new code. We're going to create a new product code. If not, we're going to call the increment sales method, which will simply increment the integer associated with that product code. And then I'm just going to have my print line, and if we go, where are we here? It should be 20 if I'm looking at my output. Where's my output? Sorry. And here we are. We're walking through. Fortunately, I can't step through it. Each product code in the map. Should be getting close. Here we go. There are the 20 product codes stored in the map and the integers. So these are the keys, and this is the value associated with that key. Pretty straightforward. Especially at this point in the game, you should understand these types of collections from a conceptual framework standpoint. We are going to take another look at an example using maps that stores user information which can ultimately be retrieved by its user ID, by using the user ID. This time we're going to use a hash map to store the users. And there are two structures, a hash map and a hash table, that I thought would be useful to discuss in a little bit more detail before we jump right into it. This is what is a hash map versus what is a hash table is a very common interview question for a Java software engineer. The first difference between a hash map and a hash table is that one is synchronized and one is non-synchronized. The hash table is synchronized. The hash map is non-synchronized. Non-synchronized means that if it's used in a multi-thread environment, then more than one thread can access and process the hash map simultaneously. So a non-synchronized structure, such as a hash map, can be used by more than one process at the same time. A hash table, on the other hand, is synchronized. And by that, it means it ensures that no more than one thread process can access the hash table at a given moment of time. And when a thread is working on a hash table, it acquires a lock, which makes other threads have to wait until the thread is done accessing the hash table. A hash map allows one null key and any number of null values. A hash table does not allow null keys or null values. There's more on the next slide. Just couldn't fit it here without making it too small for me to see. Hash map implements the linked hash map, and it maintains the insertion order and tree map sorting of the mappings based on the ascending order of the key. Hash table does not guarantee any kind of order. It doesn't maintain the mappings in any particular order. So initially, a hash table was not part of the collection framework. It has since been made a collection framework member later after being retrofitted to implement the map interface. Hash map implements the map interface and is part of a collection framework since the very beginning of Java. Another difference between these classes is that the iterator of the hash map is a fail fast, and it throws concurrent modification exception if any other thread modifies the map by adding or removing any element except the iterator's own remove method. So in more simple words, fail fast means when calling iterator.next, if any modification has been made between the moment the iterator was created and the moment next is called, you're going to get concurrent modification exception thrown. Now we're going to take a look at a fully implemented program that implements hash map. So this program, which I'm going to give you the code for, is called the user management program, and it works off of two classes, the user class and a user class. And it creates a user object that has a string, user ID, string first name, last name, pretty straightforward, right? And then users is a collection of users that is stored in a hash map. So here we go, we're instantiating a new hash map. String is the key, and then user is what's stored at each instance. And I'm going to run this program. I've got breakpoints all over the place, as you can see, just so we could take a look at what's happening. So here we're about to instantiate a new hash map, user map. I'll step over that, and then let's take a look at what we have. So there's our user map. It doesn't have anything added to it. I'm going to step into here and let's add one user. Step out of that. And now let's take a look. So we have, the key is FZIFL? FZ. I'm having a hard time with F followed by Z. FZIFL. And that is the user ID. It is also the key for this hash map. And first name is Fred Ziffel. F Ziffel. Oh, I got it. I get it now. Sorry. So let's, we're going to add another user. So now we have a couple more users, and here we are. We have Rover, F Ziffel, Geoman 57, and each one of these is has a key, and then it has the user object, and the key is the user ID for this hash map. And so we're calling the put method. We're getting the user ID from the user object, because that's going to be the key, and then we're adding the user. So, and then we're going to allow the user, no pun intended, the user of the program to search for users. I'm going to stop in debug mode so I don't have to keep going. I'm going to just run this program, and you'll see it actually running. So Appleseed, I think, was one of the users. Yes, Appleseed is Sam Geary, F-Z-I-F-F-L-E, right? Fred Ziffel. How about we do W Mink? Not in there. Okay. So there's a simple implementation of a hash map. I hope you enjoyed this. I'm going to give you the code. Obviously, you know what you need to do with this. So to summarize some of the things we've learned, the tree set and tree map classes use a tree, an underlying tree structure, to hold the elements of the set or map. These are binary search trees, and more particularly, they're red-black balance trees. And all of the basic operations are performed with O log n efficiency. So that's implementing sets and maps using trees. When we're implementing sets and maps using hashing, we use the hash set and hash map classes. An element in a hash table gets stored into a location based on a hashing function. And a hash function does some calculation based on the element itself. And in a hash function, a hash table, multiple elements might be stored in the same location. And this instance is called a collision. So we'd have a function that maps each element to a unique location called a perfect hashing function. So to get around collisions, we use a function to make sure each element is in a unique location, not shared by another element. And just to reiterate, that's called a perfect hashing function. Here we have a graphic depiction of a hash table with a simple hash function that bases placement on the first letter of the string stored in the table. And in this instance, collisions are managed using a list of A names, a list of B names, etc. So each location, if it has multiple or collisions, you'd actually have a list implemented for that location. So this brings us to the end of the chapter, but I would be remiss if I didn't give you an assignment related to hash maps. So this is a modified version of the program I was going to give you the code for, but I'm going to have you build this from scratch. Okay, so let me show you. Got the user management program, which is the driver that just presents this menu. And we're going to add user, find user, list user, remove user, or exit will be our menu options. And so we've got the simple user class, instantiates a new user. User has a first name, a last name, and a user ID. And then we have the users class, which creates a hash map of each user. And we use a string for the key. And the key is going to be the user ID. So if you come back here, you're going to have to get the user ID, use that for the key, and then the object stored in the hash map will be the user. And I don't know if add user was there. Anyway, I've got add user, get user ID, and remove user. And I'm going to run this and show you. I've left it where it manually populates the 4 or 5 users that were already in there. So if I choose list users, you're going to get those. Put them in there. Pretty straightforward. So let me add a user. Let me add, let me see, D Prescott 99 will be the user ID. It will be DAC Prescott. Okay. And so if I want to list users now, what did I press? Oh, I'm sorry. M Jones 65. Okay, so if I list users now, Monica Jones and Dak Prescott are in there. So add, if I want to find a user, that works the same as before. If I want to remove a user, let's remove Sam Geary, whose user ID is Appleseed, so that's the key. Okay, so if I'm not sure if you're seeing that, but I'm now going to list, right? And he's gone. And, you know, if I want to find a user, M. John Jones, I'll put 69, not found. And so then I'm going to exit. So I'll put a rubric up, but yes, I want to be at add user, obviously get user. So let's go over this real quick. User is just a class that creates a user, user ID, first name, last name. And get user ID gets a string, to string, pretty straightforward, and first name is a string, last name is a string, user ID is a string, and then we've got the users. Here's where all the magic takes place. This adds a hash map. Okay. And the key is a string, and the user is the element stored. I don't think I'm forgetting anything. It's pretty straightforward. I don't even have any exceptions being thrown in this. I just want you to play around with a hash map and understand how it works. Okay, thanks for watching. Obviously, if you have any questions, ping me.